The next topic we're going to focus on with respect to templates is the ability to have default template parameters. And this is something you can do only with class templates. You can't do this with function templates. You can only do it with class templates. So as you can see here, we're going to have a stack, and the stack is going to be parameterized by type T, and we're going to default the type of the stack to int. So if we don't do anything else, it's going to get an int. And then there's a bunch of other stuff here I'm not really showing you. And this particular stack is going to be implemented with a vector of T, which will default to int. All right, so let's take a look and see how this would work. So probably should, well, let's first specialize this with double. So this is going to define a stack of doubles where we explicitly put double in the use of the stack. When we instantiate the stack, we say, I want this to be a double. And then down here, we don't have anything inside the less than greater than template designator, and that will go ahead and default to int. So we'll have a stack of int by default. So a very simple mechanism, but powerful, and we'll see how it gets used shortly for very cool things for concepts such as container adapters and so on, which is another STL feature. All right, so this was a very simple example. I'm not even going to bother running it because it doesn't really do anything. It's just showing that you can do this. All right, let's move on. And we'll go ahead and talk now about some other interesting aspects of templates. So it turns out that you could also instantiate templates with more things than just types. So you can have, of course, you can have types. We've been looking at types for most of the time. You could also instantiate it with non-type template parameters, such as values. And the third thing you can instantiate a template with are template parameters. And we'll take a look at all of those things before we wrap up today. So let's take a look at some of the things you can do for non-typed parameters. You can pass in integers or enums. You can pass in pointers to objects or pointers to functions. You can pass in references to objects or references to functions. And you can also pass in pointers to members. And you can qualify these things if you want in various types of things. Non-type template parameters have some restrictions. They have to be integral values, enumerations, or instance pointers with external linkage. They can't be string literals. They can't be global pointers, since those have what are called internal linkage. And they also can't be floating points, type names, or the void type. And another thing to note here is that non-template parameters aren't L values. They're just simple data. They're sometimes called pods, plain old data. Probably should call that pod. So we like to call that pod, and that's P-O-D. In Java, they call them POJOs, plain old Java objects. So here's the couple examples of this mechanism. As you can see here, we've got a function template that takes a type T and an int v, and we call this add const n, where we pass in a value n, and then we add v to it. So that's going to be an example of a template function that's got a non-type parameter. And then you can also see we're going to have this class called memblock. And here's memblock. Memblock is going to define basically a block or an array, a one-dimensional array of memory of type T and size n. So n is passed in as an int, and then down here we go ahead and define ourselves a memblock with n elements of type T. And this interesting syntax here says set all those values to 0. Over here you can see we have a way to set an element in the memblock and then get the value of an element in the memblock. And here's just the implementation of this stuff. It's pretty obvious what you do. It's just indexing into an array. So let's go take a look at the main program. And you can see here we define memblock int 5. So that's going to be a block of memory of size 5 of type int. We then go and define a memblock that has 15 doubles in it. Those, of course, are two different types. You can't mix and match them. We go ahead and set the value at the location 0 in my ints to 100, and we set the value in my floats to 3, or the value at location 3, which is actually the 4th element, to 3.1416, the beginning of pi. Then we go ahead and print those values. And then the final thing we do here is we take an int, in this case 10, and we add 6 to it, where 6 is a parameter to the template function that's specialized with a non-type parameter. So just for kicks, let's go ahead and run this. And you can see what we get. You get what you'd expect. We get 100 and 3.1416, and then the value 16, because 10 plus 6 is 16. So once again, you might think to yourself, why are we doing all this stuff? This seems weird. It's actually not weird at all. It really sets up for very sophisticated mechanisms in C++ templates to do all kinds of cool template metaprogramming. And we'll talk more about template metaprogramming soon. It's really, really cool. So the final example we're going to look at today is another variant of template parameters that are not strictly types, but instead they're themselves template parameters. And this is what's typically called a template parameter. And in this particular case, we're going to have a template for a stack where the implementation will be passed as a template parameter. So we're going to be able to pass in some other data structure, like a vector, for example, or a list or a deque, and then have our stack implemented using that. And we're going to cross-cut this capability with the ability to have default values, so we can have our stack default to a particular template implementation. So let's go ahead and take a look at the example. I think it becomes a lot more clear once you see what it looks like. So here is the template parameter syntax. So we're defining ourselves a stack, and of course it's a stack of t, as always. And then the second parameter will be a template parameter, which in this case we've given the wholly unimaginative name container, and we've set the container to be deque, and that's one of the built-in STL containers. So you can see here what's happening is the template is going to kind of borrow the template parameter. The second parameter is going to borrow the type that we have in the first parameter. And down here, we're going to say this template parameter's name is container, and it defaults to deque. And then here are just a few of the methods. Obviously, there's a lot more that you would normally have for a stack, which we've already seen. And you can see here that we're going to define ourselves an instance of the container of type T, which we call S for the stack implementation. And then the various methods like push and pop and top will then forward. Excuse me. They'll forward to the container that we stored based on the type that was passed in. So it'll push will become push back, pop will become pop back, top will become back, and so on and so forth. And as long as the container that we passed in here conforms to those methods, which it will if it's a sequential container, then we're all set. So let's come down here and see how we can actually use this. So we're going to have a stack of strings, which will default to deque. So it'll be a deque stack of strings. And then the other parameter we're going to have here, or not the other parameter, the other variable will be a stack of ints, which uses list. List, of course, also being another sequential container in STL. So this will be a list stack of ints, and the first variable will be a deque stack of ints. And then we go ahead and do some operations here. We push hello onto our deque stack of strings. We take a look at the top element, and we print it, and then we pop the top element. And then down below, we push 42 onto our list stack of ints, and then we get the top item, print it, and then pop it. Okay, so now that we've talked about what this code should do, let's try to compile it and see if it actually does what we expect. And of course it does. It prints out hello and 42. So this is illustrating how you can have templates that are themselves parameterized by templates, and you can give default values to those template parameters as well.